In 1900, one out of every 4 trees standing in the Appalachian forest was an American chestnut. Not 1 in 100, not 1 in 50, 1 in 4. These were not small trees tucked between oaks and maples. They were giants, 80, 90, 100 feet tall, straight as columns. Wide enough that 2 men could not reach around the trunk with their arms outstretched. They ran from Maine to Mississippi, from the Atlantic coast deep into the interior of the continent. They covered the spine of the Appalachian Mountains like a living cathedral roof. By 1950, almost all of them were dead. 3 billion trees, gone, in less than half a lifetime. Entire mountains changed color as the gray standing trunks replaced the green canopy. Entire economies collapsed quietly, without headlines, without government reports. Families that had lived off these trees for generations suddenly found the land they farmed harder, poorer, and more expensive to work. And today, most Americans have never heard of it. This was not just a forest story. It was an agricultural story, an economic story, a story about what happens when a keystone species disappears and the systems built around it collapse without anyone noticing until it is too late. To understand what was lost, you have to understand what the American chestnut actually was. It was not a specialty timber. It was not a rare wood prized by craftsmen and sold at a premium. It was infrastructure. Cheap and abundant everywhere, and better than almost anything else available for the work that rural life actually required. The American chestnut grew fast. In forest conditions, it pushed toward the canopy within a decade, outcompeting slower-growing hardwoods. Unlike oak, which could take 60 or 70 years to reach usable size, chestnut gave you workable timber in 20 to 30 years. A farmer who planted chestnut on his woodlot could expect his children to harvest it. And that kind of generational return was built into the rural calendar the same way planting corn was. The wood itself was extraordinary by every measure that mattered to a working farm. It was straight-grained, which means it split cleanly and predictably. A man with a fro and a mallet could split chestnut rails all day without fighting the grain. It was lightweight relative to its strength, easier to move and work than oak. It dried quickly without the warping and checking that plagued other hardwoods. And it contained high levels of tannic acid, a natural compound that made it nearly impervious to rot and insect damage without any treatment whatsoever. That last quality is what made it irreplaceable. Farmers across Appalachia sank chestnut fence rails into the ground and forgot about them. Not for 10 years, not for 20, for generations. Fence lines built before the Civil War were still standing when the blight arrived. Telegraph companies ran their lines across the mountains on chestnut poles because they lasted longer with less maintenance than anything else available. Railroad companies laid chestnut ties across tens of thousands of miles of track because the wood held the spikes, resisted moisture, and did not need replacement every decade. When cabins and barns built from chestnut lumber still stand today across western North Carolina and Virginia, holding together without the chemical treatments that every piece of modern lumber requires just to last 15 years. Furniture makers worked chestnut because it was stable, took finish well, and produced a clean, open grain. Craftsmen building wagon wheels, tool handles, and roof shingles reached for chestnut without debate because it was the obvious choice. And then there was the tannin industry. The bark and wood of the American chestnut contained concentrations of tannic acid high enough to make it the primary raw material for leather tanning across the entire eastern United States. Tanneries ran on chestnut extract. The industry employed thousands of people across Appalachia and was worth millions annually. It was not a side business. It was a core economic pillar built entirely on one tree. Chestnut was not rare hardwood, it was infrastructure. And beneath all of that, beneath the timber and the tannin and the fence rails, there was something even more fundamental that almost no one talks about today. The American chestnut produced nuts, reliably, abundantly, every single year. This sounds like a minor footnote until you understand what it actually meant to a mountain farming family in 1880. Oak trees produce acorns, but acorn production is irregular. A strong mast year is followed by 2 or 3 lean years. Animals and people dependent on acorns had to manage through cycles of abundance and scarcity with no way to predict which year was coming. The chestnut was different. It produced a heavy, consistent crop year after year with a reliability that made it something you could plan around the way you planned around a field of corn. The nuts were high in carbohydrates, low in fat, and genuinely edible in ways that acorns are not without extensive processing. They could be eaten raw, roasted, is dried and ground into flour, or boiled into a meal that carried a family through the lean months. In parts of Appalachia, chestnut flour was a staple before wheat became cheap and widely available. Families gathered chestnuts in the fall the same way other families harvested corn, not as a supplement, as a primary food source. But the most economically significant use was not human food. Pigs turned loose in chestnut forests in the fall came out in spring fat, healthy, and ready for market. The chestnuts fell in enormous quantities across the forest floor, and the hogs converted them into meat with almost no input from the farmer. No purchased grain, no hauled feed, no storage infrastructure. The forest provided what the barn could not. Mountain farmers called it masting the hogs, and it was the foundation of the Appalachian pork economy for 2 centuries. The math was direct, and it mattered to families operating on thin margins. A farmer who ran 50 hogs through a chestnut forest from September through November could bring them to market in December without having purchased a single bushel of grain. The same farmer without chestnut had to buy feed, haul it up mountain roads, store it through winter, and accept a narrower margin on every animal he sold. The chestnut did not just feed livestock, it subsidized the entire operation. Beyond livestock, the nuts sustained wildlife populations at a scale that modern forests cannot match. Deer, black bear, wild turkey, and dozens of smaller species depended on chestnut mast as a primary food source. The reliability of the crop meant stable wildlife populations year to year, which meant consistent hunting harvest for families who depended on venison and turkey to get through winter. The tree was holding up the entire food system, cultivated and wild, simultaneously. The root systems ran deep, when anchoring steep mountain slopes against the erosion that came with heavy Appalachian rainfall. The leaf litter broke down slowly and enriched the forest floor year after year. Mountain farms that bordered chestnut forest had a buffer against runoff and slope failure that no planted crop could replicate. Chestnut allowed families to farm marginal mountain land with lower input costs and higher resilience than any alternative. It was not a luxury, or it was the margin between a farm that worked and a farm that failed. If you want to understand the agricultural systems that made rural life viable before industrial inputs replaced everything, subscribe. That is what this channel exists to document. In 1904, a forester at the Bronx Zoo in New York noticed something wrong with the chestnut trees on the grounds. The bark was cracking, orange, sunken lesions were spreading across the trunks. The tissue underneath was dying in rings that circled the tree completely, cutting off the movement of nutrients and water between roots and canopy. Within weeks of the first lesions appearing, the tree above them was dead. Scientists investigated. They identified a fungus, Cryphonectria parasitica, a pathogen that arrived in the United States on imported Asian chestnut trees, brought over by nurseries expanding their collections with exotic species from China and Japan. Asian chestnuts had lived alongside this fungus for thousands of years. They had evolved resistance to it. Their immune response contained the infection, and the trees survived. The American chestnut had never encountered it. There was no evolved resistance, no chemical defense, nothing in its biology that recognized what was attacking it. The fungus spread through airborne spores. Wind carried it. Birds carried it. It moved through continuous forest faster than any intervention could follow. By the time scientists understood what they were dealing with, the infection had already spread across hundreds of miles of unbroken chestnut canopy. There was no fire break. The trees grew close enough that the spores never had to travel far to find the next host. The fungus did not need to overcome any resistance. It simply spread and killed. A healthy chestnut would develop the first lesion, often high on the trunk. The canker would grow, the bark would split, and the crown would begin to die from the top down, leaves turning brown and holding on through winter in a pattern woodsmen called flagging. Within a few years of first infection, A tree that had stood for 2 centuries was dead to the ground. The mountains turned gray in a single generation. By the 1930s, the blight had swept through the entire range. By the 1940s, the American chestnut was functionally extinct as a canopy tree. 3 billion trees gone. Every intervention failed. So quarantine lines cut ahead of the blight were jumped by airborne spores before the saws stopped running. Chemical treatments applied to infected bark came too late. The fungus was already systemic before the lesions were visible. Selective breeding programs searched for naturally resistant individuals and found none. Nothing worked. The speed of the blight, combined with the complete absence of resistance in the American chestnut, produced a collapse that no tool available at the time could stop. In less than 50 years, the dominant tree of the eastern American forest was gone. The ecological loss was visible and it was documented. What is less visible is what it did to the farms. The cash economy built around chestnut nut gathering collapsed immediately. Families that had supplemented their income by selling chestnuts in the fall lost that income without warning and without any replacement. Born in mountain communities where nut sales represented a significant fraction of annual household cash, the effect was immediate and permanent. The livestock economy contracted. Farmers who had run hogs on forest mast at zero feed cost now faced purchased grain as a permanent expense. The price of grain, the cost of hauling it to remote farms, and the infrastructure required to store it represented a new line item in the farm budget that had never existed before. Margins tightened. Farms that had been viable became marginal. Marginal farms were abandoned. The fencing economy shifted entirely. Chestnut rails split from a woodlot cost nothing beyond labor. A farmer could maintain miles of fence using his own timber with hand tools in an afternoon. When the chestnut was gone, replacement meant purchased treated lumber or wire fencing with metal posts. Both cost money the chestnut system had never required. The tannin industry collapsed within a decade of the blight reaching the major production regions. Tanneries that had operated for generations closed. The industry shifted to imported vegetable tannins and then to synthetic chemistry. The jobs and the economic activity moved away from Appalachia and did not come back. Wildlife populations declined as chestnut mass disappeared from the food system. Deer, bear, and turkey all faced reduced autumn and winter food availability. Hunting harvests became less reliable. Families that had depended on game to reduce winter food costs found the calculation had changed. Forest composition shifted toward oak and maple in the gaps left by dead chestnuts. Oak mast is less reliable than chestnut. Maple produces nothing significant for wildlife. The forest that replaced the chestnut forest was less productive as a food system by every measure and offered lower timber value per acre over the rotations that mattered to farm woodlots. On steep slopes, the loss of deep chestnut root systems increased erosion as shallower rooted replacements moved in. The soil stability that chestnut had provided for centuries degraded gradually and permanently in many areas. The loss of chestnut quietly increased the cost of farming Appalachia across every dimension simultaneously. Not by catastrophic amounts in any single year, but steadily, permanently, and with no reversal in sight. The farmers who lived through it felt every change. Their children accepted harder conditions as normal. The generation after never knew there had been anything different. If your family farmed in Appalachia, or if you have seen old chestnut beams still holding up a barn that has stood for 100 years, put that in the comments. Those details are part of the record. Here is what most people do not know. The American chestnut is not extinct. The blight kills the above-ground portions of the tree. The cankers girdle the trunk and kill everything from the ground up. But they do not kill the roots. The root system of an American chestnut survives in the soil long after the visible tree is dead, and those roots re-sprout. From Maine to Mississippi, across thousands of locations within the original range, chestnut stumps and root systems push up new shoots every spring. Young saplings genetically identical to the trees that covered the mountains, reaching toward the canopy. Then the blight finds them. The sapling develops cankers. The trunk dies. The roots survive. New shoots come up the following spring. The American chestnut has been caught in this cycle for 100 years, perpetually sprouting, perpetually killed before it can reproduce. Millions of root systems still alive beneath the forest floor, sending up growth every year, reaching 6 or 8 or 10 feet before the blight cuts them back again. The American chestnut is not extinct. It just cannot grow up. That distinction matters practically. The genetics are intact, and the root systems are intact. The biological material needed for restoration exists in the ground right now across the original range. The tree is not gone, it is suppressed, and that suppression may finally be addressable. The American Chestnut Foundation was established in 1983 with a question that seemed almost impossible at the time. Can the tree be brought back? The first method was backcross breeding. The Chinese chestnut carries natural resistance to Cryphonectria parasitica in its genetics. Backcross breeding transfers that resistance into an American chestnut while preserving the American tree's form, growth rate, timber quality, and ecological function. The process requires crossing an American chestnut with a Chinese chestnut, selecting offspring that most resemble American chestnut in form and growth, crossing those back to pure American chestnut, and repeating this across multiple generations while testing each generation for blight resistance. After 5 or 6 generations, the resulting tree is 15/16 American chestnut genetically, while carrying the resistance trait from the Chinese parent. This is slow. Each generation requires years of growth before it can be evaluated and crossed again. And the foundation has been running this program for over 40 years and has backcrossed trees in the ground across the Appalachian range now, with results that show meaningful resistance improvement over wild American chestnuts. The limitations are real. The resistance produced through backcrossing may be incomplete. Some American characteristics may be diluted through the crossing process in ways that only become apparent at forest scale over long time periods. And the program is ongoing, and the outcomes are not yet fully known. The second approach is more direct and more contested. Researchers at the SUNY College of Environmental Science and Forestry identified a single gene that addresses the blight mechanism specifically. The gene taken from wheat produces an enzyme called oxalate oxidase. The blight fungus kills chestnut tissue by producing oxalic acid, which creates a toxic cellular environment the tree cannot survive. An oxalate oxidase neutralizes oxalic acid. A tree producing this enzyme can contain cankers rather than being killed by them. The researchers introduced this gene into American chestnut embryos and grew trees from the transformed material. Those trees, known as Darling 58, show strong blight resistance in controlled trials. Field trials are underway with results that are genuinely promising by the measures being tracked. The regulatory process is the current constraint. Darling 58 requires simultaneous approval from the USDA, EPA, and FDA for release into wild forest ecosystems. That process is ongoing. It involves legitimate questions about ecological risk that do not have simple answers, alongside the straightforward biological fact that the American chestnut cannot survive in its native range without some form of intervention. Smaller-scale reforestation trials using the best-performing backcross trees are also underway across the range. And these plantings track survival rates, growth, blight response, and integration with existing forest ecology. They generate data that will shape the larger restoration effort when resistant trees become available at the scale reforestation actually requires. To be precise about where things stand, the American chestnut has not been restored. What exists today is experimental work at early stages of what will be a multi-decade process. The timeline for meaningful reforestation is measured in generations, not years. But the biological and technical foundation for restoration exists now in ways it did not 30 years ago. That is a material change. Think forward from here. If the American chestnut is successfully restored to a meaningful fraction of its original range, the agricultural implications are direct and significant. A mature chestnut tree produces 20 to 50 pounds of nuts annually. An acre of chestnut trees at mature spacing can yield thousands of pounds of edible carbohydrate every year. With no annual tillage, no purchased seed, no synthetic fertilizer, and no irrigation beyond rainfall. The crop is perennial. The capital investment is the planting. After that, the system runs on its own biology. For livestock operations, the economics are the same as they were in 1880. Animals finishing on chestnut mass require less purchased grain. Oh no, on a working farm where feed costs are a major operating expense. A perennial calorie source that costs nothing per bushel after establishment is not an interesting idea. It is a direct reduction in input costs that flows straight to margin. For farmers working land that row crops cannot justify, land that is too steep, too thin, too rocky, or too variable, Chestnut provides a production option that almost nothing else at this scale can match. It produces a marketable food crop. It builds soil continuously through litter decomposition. Its root system stabilizes slopes and reduces erosion. It produces rot-resistant timber over a 30 to 50-year horizon as a secondary yield. It sequesters carbon in a large, long-lived canopy. Every one of those functions runs simultaneously from a single planting. Agroforestry researchers describe this as a system crop, a planting that builds value across multiple timescales and performs multiple production functions from the same land base. Chestnut pays in nuts within 5 to 10 years of planting, in timber within a generation, and in soil and ecological services from day one. For rural Appalachian communities that have been losing economic ground steadily for decades, a restored chestnut offers something that most agricultural programs do not. A perennial production system that does not require the full input infrastructure of industrial agriculture to function. A timber resource that does not require chemical treatment to last. A food system that reduces exposure to the supply chain fragility that the last few years have made visible to everyone. A restored chestnut forest would lower agricultural input costs and increase rural resilience in measurable, direct ways. That is not a sentimental argument. That is applied land economics. Somewhere in Appalachia right now, a chestnut sapling is pushing through the soil from a root that has been underground for a century. That root survived the blight by going deep and wading through every decade that passed without a mature tree above it. And somewhere in a research plot in Tennessee, or a backcross orchard managed by people who have spent decades on this problem, another tree is growing. One that might be able to survive what the wild sapling cannot. One that might finally reach the canopy, set flowers, drop nuts onto a forest floor that has been waiting for them for 100 years. 3 billion trees in 40 years. It took one generation to lose them. Getting them back will take several more. But the roots are still there. The genetics are still there. The biological foundation for what was lost is intact underground across the entire original range. The work is real. The timeline is long. And for the first time in a century, the outcome is not foreclosed. If you want to follow what was lost and what the evidence says about what might return, subscribe and turn on notifications. The next vault opens soon.